We're trying to solve this integral for odd n's.
For odd n.
For odd n.
All right.
Yeah. So first, because n could be like 99 or 2001.
Yeah.
You start by evaluating t to the 1 e to the minus kt squared dt from 0 to infinity. And let's call this integral I. Okay, now this is a fairly straightforward integral. You could do this with u substitution. So u is minus kt squared. This is, fairly straightforward integral. Du is minus 2kt dt. So if you divide by minus 2k, you would get du over minus 2k is equal to t dt. Okay, and so this becomes, and you could change the bounds if you want. So if t equals 0, plug it in the first equation, u equal minus kt squared, you get u equals 0. And if t equals infinity, then u would equal minus infinity. So I becomes the integral from 0 at 0, 0 to minus infinity of t dt is du, and 1 over minus 2k, we can just pull it out, and this is just e to the u, right? And the integral of e to the u is just e to the u from 0 to minus infinity. And if you evaluate the upper bound first, you would get minus e to the minus infinity over, let's actually do it here. So I would equal e to the minus infinity minus 1 over 2k e to the minus infinity, which is 0, by the way. E to the minus infinity is 0, minus 1 over 2k e to the 0. E to the 0 is 1, so the final answer would be 1 over 2k. Okay, so this is the integral for t e to the minus kt squared. Okay, now what you do is you find successive, you start taking derivatives for I. Why do we do that? Because look, we said that I, let me show you what the trick is here. So we said that I is equal to 0 to infinity of t e to the minus kt squared dt. And we proved at the end of the day that this is equal 1 over 2k. Now notice, if you actually differentiate this with respect to k, so if you were to do di over dk, you would get, again, you can go in with the integral inside, with the derivative inside the integral. So this would be 0 to infinity. Derivative of minus kt squared would be minus 2t minus t squared times t, right?
Right.
Minus t squared times t e to the minus kt squared dt, right? Which is equal to minus t cubed minus t cubed e to the minus kt squared dt. And what's the derivative of this with respect to k? Minus 1 over, so we're taking the derivative of this with respect to k, just like we did on the left hand side.
Yeah.
So this is minus 1 over 2k squared.
Yeah.
And so notice, this minus sign can cancel this minus sign, and you actually get t cubed e to the minus kt squared dt from 0 to infinity equals 1 over 2k squared, which is interesting. And then you can continue taking derivatives with respect to k. If you actually, so you went from t to t cubed, right? Remember, n is odd, so we're going from t to t cubed. Now we're going to go to t to the fifth. So if we differentiate this with respect to k, you're going to get, you can see the pattern here. You're going to get minus t to the 5, the derivative of the left-hand side, e to the minus kt squared dt. And here you're going to get minus 2 over 2k cubed. Right? You can cancel the minus signs, so you can make both of these a plus. And now the integral from 0 to infinity of t to the fifth e to the minus kt squared dt is 2 over 2k cubed. Now do it again, so you can see the pattern. Differentiate this again with respect to k, just like we did here. So here we took the derivative of this with respect to k. Right? So do this again. With respect to k, and you kind of get the idea. You're going to get t to the 7 minus t to the 7 e to the minus kt squared dt, and here you're going to get 2 times minus 3 over, right, 2k cubed, 2k, wait, 4. And you could again eliminate those minus signs, and this is the integral from 0 to infinity, right? And you can cross out this 2, so you get 3k to the 4. Now you can see that every time you are differentiating with respect to k, what's happening is you are getting so this was, you are getting an additional k in the denominator, and your numerators are increasing. So you went from 1 to 2 on the second derivative to 3 on the third derivative. So you kind of catch the trend. So eventually we're going to come to, if let's say we take the, remember we're getting to n is odd, we're going to get to n factorial, right?
Yeah.
Over, we have a 2 always in the denominator, because look, this here was a 3 factorial. If you think about it, 2 times 3 is 3 factorial. This was a 2 factorial. This was a 1 factorial. So on the third derivative, we got to 3 factorial. On the fourth derivative, we're going to get to 4 factorial. On the nth derivative, which will generate for you t to the n, with n being odd. So this will be 2 to the 2n plus 1, because n has to be odd. You're going to get n factorial. And in the denominator, you will get, you're always getting a 2. Notice this 2 here, right? Yeah. You're always getting a 2. And this guy is always exceeding this guy by 1. So when the numerator, when the last integer is 3, the power of k is 4. When the last integer is 2 on the second derivative, the power of k is 3. And when the first integer is 1, the power on k is 2. So this is just k to the n plus 1. And this here is e to the minus kt squared, integral from 0 to infinity. So the answer is n factorial over 2k to the n plus 1. Now, that's where the, so if you were to turn this around, that's where you get the n factorial equaling the gamma function of n plus 1, which we are discussing in chapter 11. So this basically, if you cross multiply, this becomes your gamma function, right? If you take the box, you can say 2 factorial is equal to 2k to the n plus 1 integral from 0 to infinity t to the 2n plus 1 e to the minus kt squared. You see the idea here? So that's what got us to the definition of n factorial being what it is.
Okay. All right. So that,
Oh, I forgot the dt here.
though those are all integers, so that didn't have anything to do with non-integers, right?
Right. Questions on this? So that's where the definition of the gamma function being the integral from 0 to infinity x to the n e to the minus x equaling n factorial came from.